Today we're going to focus on two different topics. First, we're going to focus on the strengths of acids using the acid ionization constant and talking about what ionization is. And then we'll move into defining more about acids and bases and what makes a strong acid and a strong base. If you're not present and you're watching this video, it means you're not watching the demonstration. So we're just going to skip through this and kind of summarize what the demonstration illustrated. So one of the things we did in our demonstration is we found what happened when we put salt into water, and we put an apparatus to test whether it was a conductor or not. And what we found is when salt was in water, it did indeed present a bright light. So the light bulb really was strong. This indicates that the ions were formed because they are what conduct electricity. Those are the electrolytes. So what we found is because the ions strongly conduct electricity, sodium chloride is a strong electrolyte. We also tested hydrochloric acid, and we found that hydrochloric acid as well produced a bright light because it ionizes completely. So when I put hydrochloric acid into water, we get that hydrochloric acid. It formed hydronium ions and chloride ions, and those ions are what, again, allow the electricity to travel and produce a charge that can light up the light bulb. Since we have ions that are produced by the electricity, HCl, hydrochloric acid, is a strong electrolyte. Since it's an acid, strong electrolytes are strong acids. In this case, we say that the reaction goes to completion. This is not a reversible reaction. The acid forms the ions in the solution, therefore lighting that light bulb brightly. An equilibrium is not established. We also tested acetic acid, and when we tested acetic acid and put that in water, we did get some ions, but the light bulb didn't light up as much. It was a very faint, so it does conduct but weakly. It will ionize, but the equilibrium will favor the reverse reaction. It consists mostly of non-conducting molecules of acetic acid. Therefore, we classify acetic acid as a weak electrolyte, and therefore, since it's an acid, a weak acid. The acid ionization constant is a value of the equilibrium constant expression for the ionization of the acid. I give an example of an acid here. Now remember, previously we learned that the equilibrium constant is represented by the products, concentration of the products over the concentration of the reactants. So in this particular reaction, we're going to put the products on top and the reactants on the bottom. But hold on, why isn't the water included? Well, remember previously we did learn that pure liquids and solids are not included in the equilibrium constant, only gases and aqueous solutions. So we totally ignore the water in this case. Take a moment here to write the acid ionization expression for acetic acid. I gave you the ionization equation. You write the expression. Did you get this? Remember, leave out the water because it's a pure liquid. All right, so let's take a look at these two examples. In the first case, HCl, notice there is no equilibrium established. It ionized completely into its ions. It's a strong electrolyte. If a strong acid completely ionizes, how will this affect the Ka? Well, remember the products over the reactants. We're going to have all of the products and pretty much no reactants. This means that my Ka is extremely large. It favors the product since it ionizes completely. If a weak acid does not ionize, how will this affect the Ka, the acid ionization constant? Well, now remember it has mostly non-conducting reactants, those molecules. So the reactants are going to be much larger than the products. It favors the reactants. So we are going to have a small ionization constant. There's a chart in your packet, and you can find these in books, that will list these ionization constants, the Ka for various acids. You do not need to memorize these. The chart will be provided. So remember, if the Ka is, in this case, if the Ka is equal to 1, then you would have the same concentration of products of reactants. If it's greater than 1, then the products are favored. And so we have, for the cases of sulfuric acid, hydrochloric acid, and nitric acid, these strong acids are going to favor the products. They have very large. In fact, we don't even put a number down. We simply write large for the Ka. If it's less than 1, it means the reactants are favored. And you can see a list there of increasing, well, actually decreasing Ka values. In other words, as you go down this list of acids, the acids are getting weaker and weaker. So let's take a look. Which is stronger, hydrochloric acid or acetic acid? Well, hydrochloric acid is listed as large, Ka, and acetic acid is listed down here, 1.8 times 10 to the minus 5. Which is stronger? Well, the hydrochloric acid is going to be stronger because it has a larger Ka value. Some acids have more than one hydrogen that can be given off when they ionize. Each proton or hydrogen ion comes off one at a time, and the ionization constant will become smaller and smaller. Let's take a look at sulfuric acid. You'll notice it has two. It's a polyprotic acid, 2 hydrogen ions. First, it'll lose 1, and then it'll lose the second one. Overall, for a strong polyprotic acid, it will lose both of them. We're going to consider that it loses both of them, although the second one will be weaker than the first. What about bases? Well, bases also have a constant Kb, which evaluates the hydroxide ion concentration, but we're not going to be using the Ka in this, or the Kb in this class. We're only focusing on the Ka with acids. So this leads us to the second part of our notes today. Let's define the Arrhenius definition of acids and bases and do some problems. First of all, we should know that acids are compounds that contain hydrogen. Well, we're going to focus a little bit more on that and say, well, those hydrogen ions produce hydronium ions. Hydronium is H3O+ in water. We can simplify this sometimes and just write it as the hydrogen ion, H+. For our purposes, we're going to use those two interchangeably. Examples of acid, you have here hydrochloric acid, nitric acid, carbonic acid, and acetic acid. You should remember how to name those. I'm not going to go through much of that today other than to say, remember they always start with an H, and if the anion ends in "ide", such as HCl chloride, it becomes hydrochloric acid. You put that stem in where the blank is. If it ends in "ate", it becomes an ic acid, so nitrate becomes nitric acid. If it ends in "ite", it becomes us acid, so sulfurous acid because it's the sulfide or sulfite ion. All right, let's take a look here at what the ionization of an acid is. In the long form, what I have, this is a general acid. HA will be the general acid. If I put it in water, it's going to form the hydronium ion plus the anion of the acid. We can simplify this and write it as a short form. The short form simply recognizes that we're putting it in water, and so we just say the acid breaks into the hydrogen ion and the anion. Let's take a look specifically of hydrochloric acid. The long form would be written like this. The short form, we're just going to put the water over the arrow. And remember, this is a strong acid, so it's going to ionize completely. There is no equilibrium in this case. One other way we can look at this is by the Lewis structure. A Lewis structure for hydrochloric acid will look like this right here. You'll notice that that hydrogen, when an acid ionizes, that proton, the hydrogen nucleus, leaves the acid and bonds with the water molecule. So we now have our anion of chlorine, or the chloride ion, with hydronium ions. Some of the strong acids that you should be familiar with is nitric acid, sulfuric acid, and hydrochloric acid. Nitric acid and hydrochloric acid are monoprotic. Sulfur, or sulfuric acid, has H2. That's known as a diprotic, and you can also have triprotic acids. These acids ionize completely in water, 100%. There is no equilibrium, so they have a very large Ka value. We've already looked at the ionization of hydrochloric acid, but here it is again, written in the short form. HCl breaks into H plus Cl minus. When we're solving problems to try to find the concentration of hydronium ions for a strong acid, we use what's called an if chart because they ionize completely. This stands for initial and final. Let's take a look here. What concentration of hydronium ions will be produced when 0.1 molar HCl is placed in water? Now remember, we have a strong acid here, so it's going to ionize completely. There's no equilibrium. And also remember, we're using the shorthand here, so the hydronium ions we're just writing as H+. According to our problem, our initial concentrations, we have 0.1 molar for hydrochloric acid, and we won't have any for our products because initially all we have is the acid. When we put it in water, however, remember it'll ionize completely, so we essentially end up with 0 for my acid, and since it's a 1-to-1 ratio, we end up with 0.1 molar concentration for both the hydronium and the chloride ions. So this is as simple as looking at the chart now and saying, what's my hydronium ion concentration? Well, it's going to be the 0.1 molar. Here's another problem. But look, we're given the grams of sulfuric acid and the liters. Remember, we need to find molarity first. So first, we're going to convert grams to moles by using the molar mass, and then solve for molarity. I've done this for you. Now, see if you can set up the if chart, and when you're ready, pause this video, and then restart it so you can see the answer. All right, so first we have to understand that this particular sulfuric acid will give 2 hydronium ions. So as I set up my if chart, we'll notice I have 0.051 molar of my acid and 0 for my ions initially. That will then switch to 0 of my acid, and since it's a 2 ratio, 1-to-2 ratio, we have to double that molarity. And for the sulfate, it'll be the same. So what's my concentration going to be? Well, there you have it. Weak acids, on the other hand, for example, acetic acid, do not ionize completely. They only ionize approximately 1%. So we do have an equilibrium. Here I list the example of acetic acid, the ionization of acetic acid in the long form. I could show you how we get this formula, but for simplicity's sake, we're just going to say to find the hydronium ion concentration of a weak acid, we need to use this formula, the square root of the Ka times the molarity of the acid. Remember, we find the Ka values from a reference table, and you have one of these provided in the chart, in the packet. So let's take a look. How do we do this? What's the hydronium ion concentration of 0.1 molar acetic acid? We're going to use this formula. From the chart, I can find that the Ka is 1.8 times 10 to the minus 5. So I plug that in. Take the Ka times the molarity in the problem, plug that in my calculator, and you should be double checking my work. And here's what I get for my answer. Your turn. You try this, put in your calculator, pause the video, and when you're done, restart the video and check your answer. We've been focusing on acids, but let's switch gears and look at bases. Bases are compounds that ionize to yield hydroxide ions in water in an aqueous solution. So in general, we get the form that the B would represent your cation. It is attached to OH, and it would ionize to produce your cation and then hydroxide ions in water. So I showed two examples there of potassium hydroxide and lithium hydroxide. Remember that for naming bases, they're salts, so they're named accordingly, just as we've done in the past with ionic substances. So NaOH, sodium hydroxide. Strong bases consist of group 1 hydroxides and group 2 hydroxides from calcium and below. So lithium hydroxide, sodium hydroxide, potassium hydroxide, those are all group 1 hydroxides. But in group 2, you'd have calcium hydroxide, strontium hydroxide, barium hydroxide would all be strong bases. These strong bases will ionize completely in water, just like strong acids do. So likewise, if I have a strong base, we're going to use the if chart, the initial final. Looking at the example, what concentration of hydroxide ions are present in 0.1 molar solution of calcium hydroxide? So first we need to write the ionization of calcium hydroxide. Notice that we have 2 hydroxides for this one, so we're going to end up getting 2 of my ions. For our initial, we have, according to our problem, 0.1 molar calcium hydroxide. And again, with a strong base, we start with absolutely none of the products. It switches to the final where I will have absolutely none of the calcium hydroxide because it ionizes completely. Again, notice we have a forward reaction only. There is no equilibrium here. For my final concentration of calcium and hydroxide, we have a 1:1 to 2 ratio. So we're going to get 0.1 for the calcium. It's a 1:1 calcium ion. And double that, 2 times 0.1 will be your 0.2 molar concentration of hydroxide. So again, here's our answer. What's my answer? 0.20 molar hydroxide concentration. For weak bases, as an example would be ammonia, anything that I did not list in the strong bases, we're going to consider to be weak bases. These do not ionize completely in water. Again, approximately 1% of it. So it really favors the reactants. In this case, it'll really favor the ammonia rather than the ammonium and hydroxide ions. The great thing about this is, although there is a Kb that would represent the products over the reactants concentration, we're not going to work on those. We're not going to do any problems with those. We're only going to work with weak acids, not weak bases. So let's look at a summary. When we're doing the problems to find concentrations of either the hydronium or H+ for acids, or the concentration of hydroxide for the bases, if it's a strong acid or base, this means it ionizes 100%. So you use the if chart. If it's a weak acid, there's little ionization. So we are going to use the formula that the ion concentration, hydronium ion concentration, is equal to the square root of Ka times the molarity. For weak bases, we're not going to do problems. This would be little ionization as well, only about 1%, but there will be no problems. All right, there's some problems for you to do. Good luck. I hope it makes some sense, and if you have questions, always ask. Have a great day.